an attempt to do a better job in terms of explaining and sharing the exact concept of spatial computing, in this video, I want to do a part 2 and use an example that Professor Miller himself used at one of his articles at the MIT News Press that has to do with the notion of baking. It is a very simplified example that does a great job in terms of explaining spatial computing. So I'm going to read from the book, and of course I'm paraphrasing here, so I hope I do a good job. As Professor Miller put it, let's imagine an everyday scenario, baking. When you follow a recipe, certain steps are universal, such as setting the oven temperature and the timing of the oven, while other specifics, like whether to bake the 350 degrees or 45 minutes, etc., change from recipe to recipe. Your brain keeps these universal steps and specific details distinct, allowing you to transfer the general process to new baking tasks without confusion. This ability hinges on what scientists call as working memory, which the brain manages through the interaction of different brain rhythms, especially beta and gamma waves. In this case, also how spatial computing manages all these cognitive processes. I'm going to keep on reading from chapter 6, where it continues that research by Professor Miller and his team at MIT reveals that beta brain waves, generally encode task rules, while faster gamma waves encode specific instances. Going back to the baking example, if you remember, if you can make the connection, these rhythms operate across the cortex with beta waves marking out spatial patches for each task rule, and gamma waves activating within these patches to encode detailed information for that specific task. This rhythmic orchestration, or spatial computing, allows the brain to distinguish between universal rules, such as in baking, and the individual pieces of information that apply to each scenario. And in a nutshell, that is what spatial computing is. Now, what could possibly be the implication of us understanding spatial computing within our brain in connection with the future generation of AI? And then I read further from the book in that the concept of spatial computing holds fascinating implications for AI and robotics, particularly as we move towards more advanced general purpose AI systems. By incorporating elements of spatial computing, AI could emulate a more human-like capacity to handle general rules and apply them flexibly to a range of specific tasks. One potential approach is to design AI systems, future gen AI, such as AGI and ASI, that incorporate spatially organized data inputs, processed at different frequencies at scale, much like the brain's use of beta and gamma rhythms indicate in spatial computing. Here, wearable devices, for example, could play a significant role if connected to real-time data streams from wearable sensors. Future generation AI could receive a constant feed of bioelectrical data, aka biointelligence data, such as neural oscillation in this case, capturing elements of human cognitive states and translating these into functional, task-oriented actions. By creating patches within its processing architecture, future AI generation could manage general procedures and specific details independently but interactively, much like human working memory. Now, like anything in this world, there's always limitation as well as challenges. So this section addresses some of those potential challenges, and it says that integrating spatial computing into future generation AI systems, however, involves overcoming several challenges. First, capturing and interpreting brain rhythms accurately requires sophisticated wearable technology capable of monitoring neural oscillation with minimum interference. AI systems must then decode these bioelectrical signals to parse out general rules and context specific details. This decoding must be accomplished in real time, ensuring that AI can fluidly shift between general tasks and specific information without lag or confusion. Another hurdle lies in replicating the brain's ability to dynamically create and dissolve task-oriented patches. In the human brain, these patches are not fixed locations. Instead, they emerge and fade as tasks demand, giving the brain immense cognitive flexibility. To achieve a similar level of adaptability, AI would need to stimulate this plasticity within its neural network architecture. This requirement is particularly complex since most current AI systems operate under very rigid structural data inputs and processes, lacking the spatial dynamicism found in human cognition. Lastly, the journey to integrate spatial computing processes into future generation AI systems such as AGI and ASI and/or robotics remains complex and full of open questions. We are only beginning to understand how neural patches are organized and control within the human brain, and it'll take significant research and technological innovation and advances to translate these discoveries into functional AI architectures. Nonetheless, spatial computing offers a compelling blueprint for creating machines capable of genuine cognitive flexibility, machines that, much like us humans, can hold onto universal principles while adapting those principles fluidly to the ever-changing demands of their environment. That's all I had for today. Hope that made sense to you all. Any question, comments, feel free to add them, and I'll see you guys next time. Thanks. Bye.